There is one thing in science that always excites and bewilders me at the same time, something most people never stop to think about. We often talk about the laws of physics, the great discoveries, the equations as beautiful as poetry, but there is one stark truth that very few people recognize. Every law in science began with a bold guess, not divine revelation or truth dropped from the heavens, just a human standing before the vast universe and saying, I think it works like this. But here's the terrifying part. When you turn that guess into mathematics, when you force it to calculate, to produce specific consequences, to confront nature, you immediately see something merciless. Even a tiny error, just a slight deviation in the data, and the entire hypothesis collapses. Science does not measure kindness. It doesn't care how strong your intuition is or how beautiful your idea seems. Mathematics forces the conjecture to stand in line, clear, quantitative, testable. And once the equation is written, there is no escape. Compared to nature, you are either right or wrong. There is no gray area, no negotiation, no I feel like. That is why I often say, science does not grow by proving things right. It grows by proving things wrong. We are not searching for perfection. We are searching for the discrepancy, because the discrepancy is the door to deeper truth. So if you want to know how humans truly unlock the universe, here is the secret. We guess, and then let mathematics judge. Nature only nods to what can survive that test. I say science begins with conjecture, and immediately many people think conjecture means vague, arbitrary, or unserious. But the opposite is true. A conjecture is unscientific only when you cannot turn it into a model that can be tested with numbers. I once talked to someone who strongly believed in alien craft, and he said, you can't prove UFOs don't exist, so you're not being scientific. Sound familiar? But science has never asked anyone to prove something does not exist. The issue is which possibility is more reasonable based on the data. In the more than 70 years since the 1947 Roswell incident, there have been tens of thousands of UFO reports, but not a single one comes with quantitative physical measurements. No spectrum, no radar, with clearly stated error margins, no repeatable coordinates. On the contrary, most of those phenomena can be explained by very terrestrial things. SpaceX Starlink satellites, with their characteristic string of lights, plasma torches from rocket test launches, or even the stealth F-117 fighter in the secretive 1980s. Between two possibilities, one, an extraterrestrial civilization crossing hundreds of light years to come here and casually violating every known energy principle, or two, humans misperceiving something under poor lighting conditions. Science chooses the second because its probability is millions of times higher, not because the first has been disproven. The same goes for extrasensory perception. If ESP really existed, mind-to-mind transmission, or predicting the future, then all of modern physics, from quantum mechanics to quantum field theory, would have to be rewritten. We are talking about breaking causality, energy conservation, and locality, which are the foundations of every equation, from Maxwell to Dirac. But when those claims are tested rigorously, like the series of experiments by J.B. Rhine at Duke University in the 1930s, or the meta-analysis by Ray Hyman and Charles Unerton in 1985, the results always return to chance levels, around 20% probability, with the Zenekard test, exactly what random guessing predicts. There is no mathematical signal rising above background noise. Things that sound right, in stories, UFOs, ESP, special powers, collapse the instant we force them to answer the question every serious scientific theory must face. Where are your numbers? Where is the predictive model? Where are the measurement uncertainties? Where is the statistical probability? No math means no prediction. No prediction means no testability. And if it cannot be tested, we are no longer talking about science. That is the simple but powerful reason. In science, you don't need to prove something doesn't exist. You only need to demand that any idea become a computable, testable model. And if it fails that test, you don't have to do anything. Mathematics will reject it automatically. In mathematics, you can prove a proposition true with absolute certainty. True today, true tomorrow, true 1,000 years from now, as long as the axioms remain unchanged. But in natural science, the rules are completely different. We can never prove a theory is true forever. We can only tentatively accept it as long as no experiment has refuted it. This is the point that confuses many people. They think that because science uses math, science can achieve the same certainty as mathematics. But science has to face nature, and nature never signed a contract, promising it will always behave according to the model we propose. Take Newton as a beautiful example. In 1687, when Newton published the Principia, his law of gravitation became the jewel of science. It described the motion of the sun, planets and moons with stunning accuracy, and for more than 200 years, no observation was strong enough to topple it. Even the calculations of Halley's comet, orbit in 1758, further strengthened Newton's reputation. Everything matched almost perfectly. But then, toward the end of the 19th century, people noticed a tiny deviation in Mercury's orbit, only about 43 arcseconds per century, small enough to seem unbelievable, yet too large to ignore. And it was mathematics that exposed that discrepancy. If you use Newton's equations to predict Mercury's position, every time it passes perihelion, the orbit precesses more than observed. No philosophy, no debate, just one number that didn't match. That small discrepancy was large enough to show that Newton did not fully describe reality. Then in 1915, Einstein's general relativity explained that exact 43 arcseconds perfectly. No more, no less, hitting precisely where Newton failed. This is not merely the victory of one theory. It is proof of the nature of science. A theory is correct only in the sense that it has not yet been proven wrong within the range. We can test. Mathematics acts as a microscope that reveals every tiny discrepancy. An experiment is the supreme judge. It doesn't care how beautiful the theory is. It only answers matches or does not match. Even Einstein was not exempt. General relativity has passed many tests, from the 1919 Eddington experiment to the modern Einstein rings observed with telescopes. But it has not been proven absolutely true either. An anomalous observation at quantum scales tomorrow could force us to adjust it, and that is beautiful. Science is never closed, never finished. It is always open to revision. So when you ask, is this theory true? The most honest scientific answer is always, it has not yet been proven wrong. That's it. Science does not promise you eternal certainty. It only promises that anything that survives for a long time has endured countless tests, thanks to the precision of mathematics and the rigor of experiment. And this is the next reason science cannot rely solely on everyday language. It is so ambiguous that it becomes completely helpless when trying to describe nature rigorously. You can say attractive force goes fast, very small, natural motion. But those phrases carry zero quantitative information. They sound scientific, but when you put them into an experimental context, they become empty shells. You cannot measure natural. You cannot calculate very small, and fast can mean anything. From 10 kilometers per h to 100,000 kilometers per h, depending on the speaker's mood. Nature does not operate on words. Nature operates on laws. And those laws take the form of equations. If I say to you two objects attract each other, as people did for thousands of years, you would immediately ask, how strongly? How much does it decrease when distance doubles? Does it depend on mass? Words cannot answer, but Newton's equation answers every single question without ambiguity. Force is proportional to the product of the masses and decreases with the square of the distance, period. No poetry, No philosophy, just numbers. And thanks to those numbers, we can predict the future of an entire solar system. If you try to replace math with everyday language, you immediately see how useless it is. Imagine trying to predict a solar eclipse with descriptions like the moon sometimes covers the sun when it moves along its natural path. You would never know on which day the eclipse occurs, how long it lasts, or where it is visible. But applying Kepler's and Newton's equations, we instantly know the exact second of the eclipse, like the total solar eclipse on April 8, 2024, predicted accurately, decades in advance, wrong by not even a minute. Language describes, mathematics predicts. That is the difference between storytelling and science. A writer can say, the electron is very small, and it sounds reasonable. But in physics, we need to know what small means. The electron's size is below 10 circumflex minus 18 meters, according to current measurement limits, a number that allows us to calculate everything from collider energy scales to atomic structure. Without that number, you cannot test anything or look at Earth's motion. If I say Earth orbits the sun at very high speed, you can form a mental image, but you cannot build a GPS satellite based on that image. But when I say the speed is approximately 108,000 kilometers per h, and the orbit is an ellipse with a semi-major axis of 149.6 million kilometers, you don't just understand the motion. You can calculate Earth's position on January 1st, 2050 at 0 o'clock UT with an error of only a few tens of kilometers. No sentence can do that. Every time you use words without mathematics, you abandon the precision that nature demands. Nature does not care whether you feel something is fast, large, approximately correct, or looks like. Nature only cares whether your model matches reality down to the last decimal place. And that is why every mature scientific field ends up written in equations. Planetary motion with Newton's and Einstein's equations. Electromagnetism with Maxwell's equations. Quantum mechanics with Schrodinger's and Dirac's equations. Thermodynamics with equations of state. All of them rest on mathematics, not because physicists like to make everything complicated, but because without mathematics, you cannot distinguish between a correct idea and an appealing but empty story. No math, no test, no falsification, and you no longer have science, just stories people tell each other. And when you start seeing the world through that lens of precision, you realize an even deeper truth. Nature does not merely obey mathematical laws. It computes everything continuously, everywhere, all the time, with a precision no human supercomputer can match. Every physical interaction you have ever heard of, from gravity to electric fields, from optics to particle motion, carries a mathematical structure so tight that changing even one small parameter would make every phenomenon behave completely differently. The Coulomb force between two charges decreases with the inverse square. If it decreased linearly, atoms would not exist. Gravity keeps Earth orbiting the sun with an acceleration of 0.006 1/s squareds. If that number changed by even 1 part in 1,000, planetary orbits would become chaotic. Nature does not work with words. Nature works with relentless calculations. Calculations so precise that however well we simulate or predict, we are only reproducing a tiny fraction of the real computation. The universe performs every second. I like to joke that nature computes in its own way. We just try to imitate, but it is not a joke. It is a fundamental truth. When two electrons repel each other, you can imagine they sense each other and push apart. But what is really happening is a quantum electrodynamics equation being executed. Millisecond by millisecond, interaction by interaction, probability amplitude. By probability amplitude. When water waves spread across a lake, you can say the water ripples, but what is actually happening is the solution of the wave equation. Every ripple, every small disturbance is the result of a calculation. Nature is continuously performing. When light bounces off a mirror, you see your reflection and think it is just reflection. But in reality, nature is quietly computing according to QED rules. Light chooses the path with the largest integrated amplitude among infinitely many possible paths. It doesn't need meetings or discussion. It just does the math instantly. Even everyday processes you don't notice, like a falling leaf or a chain of computations. Aerodynamics, gravity, torque, drag, turbulence. Every second nature processes billions of variables you never see. And the extraordinary thing is, it never makes a mistake. No rounding error, no bugs, no logical mistakes. Nature does not try. It operates according to the mathematical system that is its very essence. This leads to an important conclusion. If we do not use mathematics, we cannot keep up with the universe. You can describe ocean waves with poetry, but you cannot predict tide times without the Navier-Stokes equations. You can talk about light as a stream of energy, but you will never calculate the colors of a rainbow without the refraction formula. You can call atoms tiny billiard balls, but you cannot predict the structure of the periodic table without the Schrödinger equation. Every time you replace math with feeling, you step out of science and into storytelling. And clearly, the universe does not run on stories. When I study QED, one of the things that amazes me most is the almost absurd precision of mathematics in describing nature. The QED calculation of the electron's magnetic moment matches experiment to 12 decimal places. That is not human cleverness. It is because nature actually computes that way. We are just copying. So if you look broadly, you realize mathematics is not merely a convenient tool scientists use to model the world. Mathematics is the world at its deepest level. The equations do not merely describe how nature behaves. They are how nature behaves. The universe does not need us to read the equations. It executes them every moment. And that is exactly why, if you want to understand the universe, you cannot skip mathematics. Mathematics is not a translation of nature. It is the native language of nature, the language the universe has been using for billions of years before humans appeared to learn how to read it. There is one moment in the history of science that I always consider one of the most spectacular unveilings of the universe. The moment James Clerk Maxwell wrote his 4 equations in 1865 and unintentionally revealed the secret of light, a secret no human had ever seen with their eyes, but mathematics saw instantly. The most wonderful thing is that Maxwell did not set out to explain light. He was only trying to describe how electric and magnetic fields change over time and space. But when those equations were written down, when you sat down and arranged them, something strange happened. From the equations themselves emerged a prediction no one had asked for. If you combine 2 of them and let mathematics do its work, you get a wave equation. It is the wave equation, the familiar mathematical form that describes water waves, sound waves, elastic waves, and the coefficient that appears in the equation when you plug in the experimental electromagnetic constants of the time turns out to be approximately 299,792,458 ml, tops exactly the speed of light. Imagine you are Maxwell in that moment. You are not observing electromagnetic waves with your eyes. You have no radio, no radar, no microwave oven. You only have 4 equations and a cup of Scottish tea. But mathematics tells you, hey, light is not some mysterious thing. It is just an electromagnetic wave traveling through space. A physicist could spend a lifetime describing light in words. Light spreads, light oscillates, Light is like tiny sparks of fire. But with vector mathematics alone, Maxwell saw the true nature of light long before humans ever saw radio waves or X-rays. It is hard to convey that astonishment in ordinary language. It is as if you solved a math problem and suddenly the equation answered, "Oh, by the way, here is the real structure of the universe. No need to thank me." The interesting part is that if Maxwell had not used vector mathematics, things like divergence, curl, gradient, the entire truth would have remained hidden in darkness forever. There is no way to describe the curling of magnetic fields or the generation of electric fields in ordinary language. No one could write a paragraph describing the phenomenon that would yield electromagnetic waves. You could say electricity creates magnetism. Magnetism creates electricity. And it sounds nice, but the crucial part is how much, where, how it changes, at what rate. And that is something everyday language simply cannot handle. But mathematics can. Mathematics does not just describe, it forces you to confront the real structure. It is the microscope of the intellect. It lets you see what cannot be seen with the eyes. The beautiful point here is Maxwell did not guess that light is an electromagnetic wave. Mathematics told him so. And when Hertz produced radio waves in 1887, more than 20 years later, nature was merely confirming what mathematics had already seen long before. I always feel excited when I tell this story to students because it proves something important. If you listen to mathematics, it will tell you secrets that nature has never revealed in any directly observable form. In classical mechanics, you can watch an apple fall and then write the equation. But in electromagnetism, you cannot see electric or magnetic fields with your eyes. Mathematics is the additional sense organ humans invented to look into the invisible parts of the universe. And when it works well, it does not just describe what we see, it shows us what we didn't even know we were missing. This brings us to the unavoidable conclusion. Mathematics is not a report about nature. It is nature at its most abstract level. Light does not obey Maxwell's equations. It is the solution to Maxwell's equations. Space does not follow Riemannian geometry. It is Riemannian geometry. When you write a physical equation, you are not describing the universe. You are reading the universe. And if you want to see what eyes cannot see, ears cannot hear, and intuition cannot grasp, you need mathematics. It is the microscope of the intellect. And Maxwell was the first person to truly use it to look straight into the invisible structure of light, something humanity had observed for thousands of years, but no one understood until mathematics spoke. You don't have to go as far as light to see the power of mathematics. Just step down into the world smaller than the atom, and you will immediately realize that human intuition completely fails. We evolved to see rocks, trees, the movement of animals, things vastly larger than the scale of the quantum system. So when you descend to the nanometer scale, your intuition is not just useless, it is actively misleading. You can picture a ball flying from A to B along a single curved path. But an electron does not do that. It travels along every possible path simultaneously. And what determines where it appears is the interference between probability amplitudes, a concept that no sentence in ordinary language can accurately convey. You have to write the equation. The Schrödinger wave function does not say the particle is here a little, there a little. It describes the entire probability structure of the physical system, an object that spreads out in mathematical space, not in everyday language. When you say the particle has a chance of being here, that statement carries no precise meaning. But when you write the equation, you are stating a measurable, verifiable, predictable number. Language cannot do that. Mathematics can, and it does it extremely well. The pinnacle of this counterintuitive reality is the path integral I once presented. Nature does not choose the shortest path, as in classical mechanics. It tries every possible path, from smooth curves to absurd zigzags. Each path contributes a complex amplitude, and the sum of those amplitudes is the probability of finding the particle at a given location. Nature performs an infinite survey of all possibilities, never making a mistake, never getting confused. Try describing this in ordinary language. You immediately fall into a loop of meaningless phrases, like it's here and there at the same time. It takes every path. The particle collapses. Random, but not random. No words can keep up with the precision mathematics provides. Why? Because quantum reality itself does not obey your intuition. The problem is not that mathematics makes quantum mechanics difficult. It's the other way around. Quantum mechanics is inherently difficult. So only mathematics is flexible and precise enough to describe it. An electron does not have an orbit like a planet. It has a wave function. Spin is not spinning in the classical sense. It is a two-valued mathematical quantity represented by a vector in Hilbert space. A photon does not choose one slit in the double slit experiment. It interferes according to complex amplitudes. Trying to express these things in everyday language is a disaster. You will either oversimplify and be completely wrong, or you will try to use vague metaphors that make everything unnecessarily mystical. But when you write the mathematics, everything becomes clear. The wave function evolves according to the Schrödinger equation. The particle has a probability of appearing. Amplitudes add up via the path integral, and everything can be verified by experiment. The wonderful thing about mathematics in quantum mechanics is that it not only describes bizarre phenomena, but predicts them with astonishing accuracy. The Lamb shift, the tiny energy level shift in the hydrogen atom, was calculated using QED with an error of less than 1 part in a billion compared to experiment. The electron's magnetic moment anomaly is predicted to 12 decimal places. No human intuition has ever achieved that level of accuracy, or even come close. That is why quantum mechanics is the perfect example for the argument. Mathematics does not make the world harder to understand. The world is hard to understand, and mathematics is simply the only language fast and precise enough to keep up with it. If you rely on feeling, quantum mechanics is chaos. If you rely on mathematics, it becomes orderly, precise, and reliable to an almost supernatural degree. So when someone says, "I don't like math, I just want to understand quantum mechanics with intuition," you can smile a little, because our intuition was built to survive in the forest, not to describe electrons. But mathematics is different. Mathematics can enter the world where particles exist in multiple states, where probabilities interfere with laws, where infinite paths collectively determine the outcome. Mathematics is the pair of eyes we use to look into a universe too small, too fast, too strange for any biological sense organ to grasp. If you feel that all this quantum stuff just seems unnatural, don't worry. It's not your fault. It's the fault of your brain. Humans did not evolve to do mathematics or to understand the ultra-small structures of the universe. We evolved to tell stories, recognize faces, avoid predators, find fruit, and guess other people's intentions. None of our ancestors needed to know second derivatives to survive the Ice Age. So the brain, quite reasonably from a survival perspective, prioritizes what I call feels right, the thing that makes a coherent story more convincing than an accurate formula. You are more likely to believe objects fall because they want to find their natural place than to believe in an acceleration equation. You are more likely to believe light chooses the most beautiful path than to accept that it tries every path in space and interferes via amplitudes. The brain loves compact, simple, memorable stories, but nature does not care what you like. It does not care what feels right. It only operates according to its own laws. You cannot beg the universe to simplify its equations, to match hunter-gatherer intuition. And this is where mathematics becomes humanity's secret weapon. While the brain demands easy-to-swallow stories, mathematics forces you to confront reality as it actually is, unambiguous, unemotional, not based on first impressions. Mathematics makes you answer the questions. Intuition avoids how much, where, according to what rule, with what uncertainty. It forces you to measure, to calculate, to verify. Your brain may not like precision, but nature loves precision. Gravity does not change because you feel it is stronger or weaker. Electrons do not change their interference amplitudes because you dislike complex numbers. Light waves do not stop obeying Maxwell because you find the equations hard to understand. And precisely because the brain was not designed for mathematics, the things mathematics reveals often feel strange to us. But make no mistake, the strangeness is not in the mathematics. The strangeness is in the universe. Mathematics is simply the only tool precise enough to peel away the shell of intuition and reveal the true structure of nature. I sometimes tease my students by saying, if you find quantum mechanics unreasonable, that's a sign you're still thinking with your Stone Age brain. But if you find the equations reasonable, that's a sign you're slowly upgrading your software. It's the kind of humor I like because it's also true. We were not born to understand the universe with mathematics, but mathematics is the only way to overcome our own evolutionary limitations. Without mathematics, you only have stories, and stories, no matter how compelling, will never take you to the heart of truth. Once you understand that our brains love coherent stories and hate precision, you will immediately see why so many half-philosophy, half-science ideas sound nice but are completely useless when confronted with nature. They float in a fog of beautiful but empty language. Life force controls the body, harmonious energy in space. The universe wants balance, so everything happens for a reason, and dozens of phrases that sound like narration in a low-budget documentary. Those statements give a feeling of depth, but try bringing them into a laboratory. They burst like soap bubbles instantly. How many newtons is life force? How does it decrease when the body is tired? Is there a unit of measurement? How many joules per hour does harmonious energy increase if I meditate? Is there a coefficient, a time curve? The universe wants it. Since when? And what does the desire time graph look like? If you can't answer, you are not doing science. You are telling philosophically pleasing but harmless stories. Science does not distinguish by sounding smart or by rhetorical skill. Science distinguishes by predictive power. If you cannot calculate something, you cannot predict it. If you cannot predict it, you cannot test it. If you cannot test it, you cannot be wrong. And if you cannot be wrong, you do not belong to science. This is not a personal opinion. It is the foundational structure of the scientific method. Imagine you say, the body is healthy when energy is harmonious. It sounds nice, but try using it to predict a number. What will tomorrow's blood sugar level be? How will body temperature differ? Will blood pressure rise or fall? You cannot. You have no mathematical model, no parameters, no quantitative relation. So the statement can be true, can be false, can be true on Monday and false on Tuesday. It is never forced to confront experiment. A theory that cannot be wrong also cannot be right. It simply floats in a region science cannot reach. In contrast, take any serious scientific theory, the ideal gas law, Maxwell's equations, The Schrödinger equation, general relativity, every one of them gives you a formula. You plug in numbers, and it answers pressure will be this, electric field will be this, probability will be this, light will bend like this, and when experiment says otherwise, the theory falls. This is exactly what gives science its power. Correct theories are correct, not because their creators were brilliant, but because they survived millions of brutal punches from experiment. Vague theories are never punched. They just stand outside the ring, commenting on the fight. You can hear someone say everything happens because the universe wants it, and you will never know whether that statement is true or false, because it cannot dialogue with reality. It is never forced to answer how much, when. Why correct in this case, but wrong in that case? It is a lullaby, not a scientific model. And the funniest part is precisely because vague theories cannot be wrong, they also cannot lead to any discovery. No one built radar from harmonious energy. No one launched spacecraft using life force. No one discovered the electron, thanks to the universe wants it. All technology, every advance from telephones, MRI, GPS, to quantum mechanics, began with an equation. No equation, no prediction, no prediction, no verification, no verification, no science. When you see why vague models always fail, you will understand a slightly hard to swallow, but extremely important truth. Mathematics is the only tool that keeps us from deceiving ourselves. The human brain is optimized for survival, not for truth-seeking. It loves smooth stories, familiar images, explanations that feel right, even when they are completely wrong. But equations do not indulge anyone. They do not care which result you prefer, do not care what makes you comfortable, or what seems reasonable. They answer only with logic and numbers. And it is precisely that indifference that makes mathematics the most powerful illusion detector humanity has ever had. You might believe hot gas naturally runs from cold to hot. If you don't think carefully, intuition does not object, because it has no mechanism to analyze. But the equations of thermodynamics object immediately. Entropy increases. There is no spontaneous energy rearrangement, just to make your intuition feel better. You might think electric and magnetic fields are two separate things acting independently, but Maxwell's equations need only a few lines to say, no, my friend. They are the same entity expressed in two different forms, and if you change the reference frame, you will see them transform into each other. No human intuition ever discovered that on its own. You can look at measurement data and feel that the curve matches the model you like, but mathematics with statistics, least squares, error estimation, will tell you that feeling is an illusion. It will measure standard deviation, analyze confidence, find systematic error, and if your model is wrong, it will expose that truth without the slightest mercy. One example I always love comes from electrodynamics. When you calculate the radiation from an accelerated charge, intuition tells you a strongly oscillating charge emits strong waves, an idea that is not wrong, but insufficient. Mathematics forces you to get it right. Radiation intensity is proportional to the square of acceleration. The emission pattern is dipole, and the entire energy distribution must obey energy conservation at every point in space. You can guess wrong. Intuition can be wrong, but the equation cannot. Or look at error analysis in experimental physics. When you measure a quantity, intuition can make you subjectively think the result looks good. But mathematics asks, good by how much? 1% error or 5%? Is there background noise, temperature dependence, 95% confidence, or 99%. Intuition cannot keep up with those questions, but statistics can. It forces you to look at what you don't want to see. You are not as certain as you think. And this is the point I love telling students. You are the easiest person to fool, but mathematics is not fooled. Mathematics is a brutally honest friend. It does not try to protect your feelings from the truth. It does not invent beautiful stories to reassure you that the universe is simple and understandable. It does not help you hold on to false beliefs just because you've held them for so long. When you write an equation and it doesn't match the data, mathematics does not offer excuses, does not lie politely, does not cover up mistakes. It says wrong, and that's it. You must correct, rethink, abandon the illusion you yourself created. This is the step many people dislike, but it is exactly the step that makes science more reliable than any other system of thought. So whenever you find mathematics dry, rigid, or uncomfortable, remember that it is precisely that rigidity that has saved us from countless illusions intuition creates. Mathematics is not your enemy. It is the last line of defense between you and your own self-deception. Mathematics, with all its beauty and power, is a self-consistent logical system. If you accept the axioms and follow the rules of inference, you will always arrive at the correct result within that system. But this very feature leads to a fairly common misunderstanding. People think that because mathematics is always correct, any mathematical description of nature must also be absolutely correct. No, absolutely not. Mathematics is always correct, but a mathematical model is only correct when it matches nature within the range in which it has been tested. If you use the wrong mathematics, or use the right mathematics, but the wrong physical model, nature will reject you in an instant. This is why we have so many different kinds of mathematics in physics. Euclidean geometry works for flat planes, but fails to describe a sphere. Classical calculus works for smooth systems, but fails at turbulence. Linear algebra suffices for three-dimensional space, but quantum mechanics requires infinite-dimensional Hilbert space. The mathematics does not change. Nature's demands change, and we must choose the appropriate mathematical tool to read it. Newton provides the perfect example. Newton's gravitational equation works beautifully at low speeds and weak fields. It accurately describes planetary motion, Cannon trajectories, satellite orbits. From 1687 to the late 19th century, it was regarded as the absolute truth of the universe. But when the astronomer Urbain Le Verrier carefully calculated Mercury's orbit in 1859, he discovered a tiny discrepancy. Mercury's perihelion advances faster than Newton predicted by about 43 arc-seconds per century. Not 40, not 50, exactly 43, a number so small that intuition would dismiss it as noise. But mathematics does not. That tiny discrepancy was enough to prove that Newton's model, no matter how beautiful, was not complete enough to fully describe nature. Then Einstein appeared with general relativity in 1915, a completely new mathematical model based on curved Riemannian geometry instead of flat Euclidean space. And when Einstein plugged Mercury's discrepancy into his field equations, the result came out exactly 43 arc-seconds, no more, no less. At the same time, Einstein predicted that light would bend when passing near the sun, a prediction that never came from Newton. And in 1919, during the solar eclipse observed by Eddington, nature confirmed that Einstein was more correct than Newton. But the important point is both used mathematics. Einstein simply used the right kind of mathematics for that case. So when we say Newton was correct, we really mean Newton was correct in the regime of low speeds and weak fields. When we say Einstein is more correct, we mean Einstein is correct over a wider regime where space and time are curved. And tomorrow, if we discover a case where Einstein fails, say at extremely high energies, we will again have to find new mathematics. Not because mathematics is wrong, but because our current mathematical model is not yet sufficient to describe nature. In this way, mathematics is like a set of truth-filtering lenses. Each mathematical model is a lens, and each lens shows you a portion of the universe with a certain sharpness. Newton is an excellent lens for most familiar motion. Einstein is a better lens when you look at black holes or light around the sun. Quantum mechanics is the required lens when you enter the atom. But no lens is the final lens. Nature can always demand a new kind of mathematics, a new structure, a new abstract space. And our task is to find the most suitable lens. Mathematics is always correct within its own world. But for it to be correct in the world of nature, we must choose the right kind of mathematics, the right model, the right assumptions. And because the universe is larger than any axiomatic system we can devise, there will always be regions where the current lens cannot see clearly. That does not make mathematics weaker. It makes science stronger, because it reminds us that truth is not something we declare, but something we approach one new lens at a time. There is one question that has tormented both scientists and philosophers for decades. Why does mathematics fit nature so perfectly that it sometimes seems as though the universe was written in equations? The physicist Eugene Wigner called this phenomenon the unreasonable effectiveness of mathematics. Unreasonable because no one understands why symbols that humans invented in their heads, on paper, in their studies, can describe the behavior of electrons, the motion of planets, or the structure of space-time. Stop and think for a moment. Mathematics is not something nature handed to us on a platter. It is something we invented, and yet for some mysterious reason it matches almost perfectly with the way nature operates. You write an equation based on pure logic, never having confronted a single experiment, and nature says, yes, that's exactly right. This doesn't happen once. It happens over and over again to the point that it feels suspicious. Dirac wrote his equation in 1928 simply to combine quantum mechanics with special relativity, a purely mathematical problem. From that equation emerged a particle. No one had ever seen, the positron. And just a few years later, in 1932, Carl Anderson discovered the positron exactly as predicted. You have to ask, why does something that started on paper and pencil correctly guess the material essence of the universe? Or consider the constants that appear in the equations: the speed of light, Planck's constant, the gravitational constant, strange numbers that act like nature's secret codes. Who put them there? Why do they have values precise to dozens of decimal places, so that every structure in the universe remains stable? If they changed by just 1%, you and I would not exist. This is what made Wigner call it unreasonable. Mathematics is not merely useful, it is unreasonably useful, to the point that it looks less like a tool for describing the universe and more like the very skeleton of the universe itself. I once told my students that if extraterrestrials exist, the first thing we could share with them would not be language or culture, but mathematical laws. Because if they live in the same universe, they too must obey Maxwell, Schrödinger, Dirac, Einstein. And if they are intelligent, they too would discover those same equations, even if the symbols they use look different. This suggests that mathematics is not a subjective human product. It is the way nature operates, and we are merely trying to decode it. You might think of mathematics as the language that describes the universe. But when you look deeper at examples like QED, predicting to 12 decimal places, or general relativity, predicting time dilation precise enough to make GPS work, you start to wonder, how can a descriptive language be this accurate? No ordinary language works perfectly like that, unless it is no longer a descriptive language, but a structural language. We do not use mathematics to describe the universe. The universe uses mathematics to describe itself, and we are just learning to read it. And when I say this, don't think I'm being philosophically flowery. I'm just looking at the facts and laughing, because it's so strange. Why do the imaginary curves of Riemannian geometry match exactly the way light bends around the sun? Why do the complex wave functions of quantum mechanics predict the exact colors of the helium atom? Why does the abstract mathematics of Lie groups describe elementary particles? If this is mere coincidence, then the universe is the greatest comedian of all time. But what if it isn't? Perhaps nowhere is the seeing ahead of reality, power of mathematics, more evident than in the classic stories of physics. Those moments when equations precede experiment by decades, even generations. When Maxwell finished his 4 equations in 1865, he did not know they were telling him something far bigger than electricity and magnetism. They predicted the existence of electromagnetic waves, oscillations propagating through space at exactly the speed of light. Maxwell, with the calm of a Scottish man who liked tea and mathematics, simply wrote at the end, "It seems light is an electromagnetic disturbance," an understatement so modest it's almost funny when you realize he had just predicted radio, radar, microwaves, Wi-Fi, Bluetooth, television, telecommunications, satellites, all in one go, without ever seeing any of those waves. And sure enough, 22 years later, in 1887, Heinrich Hertz first produced radio waves in the lab and confirmed what Maxwell had heard from mathematics. Hertz said, "I do not think this has any practical use," one of the most mistaken statements in human history. But let's forget radio for a moment and go to an even bolder prediction, Dirac's equation of 1928. Dirac was simply trying to marry 2 things no one had married before: quantum mechanics and special relativity. He set a very mathematical requirement. The electron equation must be linear in first derivatives and must preserve Lorentz form. Something strange happened. The equation did not just describe the electron. It also had a negative solution, a particle with positive charge, but the same mass magnitude. Dirac didn't know what to do with it, but mathematics insisted, hey, besides the electron, there is another particle exactly like it, but with opposite charge. 3 years later, in 1932, Carl Anderson observed the positron in a cloud chamber with exactly the mass and properties the Dirac equation demanded. Let that sink in. An equation conceived in one human mind in 1928 pointed to the existence of a form of matter no one had ever seen on Earth. No storytelling, no intuition, no initial observation, just mathematical structure. But perhaps the most beautiful example of mathematics leading the way in physics is still Einstein. When he wrote General Relativity in 1915, he had no pictures of black holes, no infrared telescopes, no gravitational lensing data from galaxy clusters, no cosmic microwave background maps. All he had was an idea. Space and time are not a static backdrop, but a geometric structure that can curve. And he chose the only mathematics rich enough to describe that structure: Riemannian geometry. From the twisting symbols of Christoffel symbols, the metric tensor, and the field equations emerged a bizarre prediction: light would bend when passing near a massive object. Remember, light has no mass. It does not fall. No intuition leads you there, but mathematics did. And in 1919, during a total solar eclipse, Eddington observed the deflection of starlight passing near the sun and found it exactly as Einstein predicted. 1.75 arc seconds. Nature smiled and said, "Correct, my friend Albert." The greatness here is not just that Einstein was right, but that he was right before the universe checked him, because mathematics had already said so. And you know what's even more interesting? The prediction of black holes. The Schwarzschild solutions of the field equations was also purely a product of mathematics. No one had seen a black hole in the early 20th century. No one knew if they were real, but mathematics said, if this equation is correct, there will be points where space-time curves to infinity. In 2019, humanity took the first photograph of a black hole. Once again, mathematics saw it first. This is not coincidence. This is the nature of physics. Mathematics sees what the naked eye cannot. If you wait until the universe provides visual evidence, you will arrive decades behind mathematics. When Maxwell wrote his equations, radio waves did not yet exist for human eyes, but they existed for mathematics. When Dirac wrote his equation, the positron did not yet exist for experiment, but it existed for mathematics. When Einstein wrote the field equations, curved space-time did not yet exist for telescopes, but it existed for mathematics. So what is the conclusion? If intuition is our primitive pair of eyes, then mathematics is our second pair of eyes, a pair that sees through time, into things that have not yet happened, into realities not yet observed. It does not wait for the universe to reveal its secrets. It unlocks those secrets first and lets experiment confirm afterward. In physics, mathematics does not merely describe the world. It leads us to places our senses could never reach. Creating a new equation may sound like the divine work of superhuman minds, but in reality, it begins exactly as I said from the beginning, with a conjecture. But understand this clearly. A guess without mathematics is just a hunch. A guess with mathematics is science. A new equation never emerges from statements like I feel the universe should work this way, or I think particles might behave like that. Those may inspire, but to become physics, you must turn the hunch into mathematical structure, a model with rules, symmetries, boundaries, and predictive power. That is where mathematics enters like a steel framework that forces every idea to obey logic. When you want to modify an old theory, you must know exactly where and how it fails. For example, if the equation fails at high energies, you must consider expanding the model by adding new fields, as the electroweak theory added the W and Z bosons. Or you can try introducing new symmetries, like gauge symmetry, leading to the modern standard model. You can also change the number of spatial dimensions, as string theory expands space from 4 to 10 or 11 dimensions to resolve singularities. Or more subtly, you change the approximation regime. For example, quantum mechanics reduces to classical mechanics when Planck's constant approaches zero. All these ideas must pass one single test. Can you write the equation? If you cannot write it, you do not have a theory. You have only a feeling. I once used a fun example. Imagine you are trying to open a mathematical safe. You know the secrets of the universe are inside, and your task is to find the correct combination. Someone who doesn't understand the process would say, why not just try October 20th, 30? But a physicist knows you cannot guess randomly. You must rely on the structure of the safe, the number of gears, the sensitivity, the locking mechanism, and reason out which combinations are plausible. In physics, that safe is the set of principles, symmetry, conservation, simplicity, compatibility with classical limits, continuity under parameter variation. Trying to guess a completely new equation without these principles is like trying to crack the safe without knowing how many digits it has. Most of the time, 99%, mathematics will reject you in just a few steps. This is why letters I receive saying you should replace gravity with a swirling energy field, or electrons are actually bubbles of time, fail at the very first step. There is no equation, no formula, no calculation, no prediction, no verification, not science. It's that simple. But when you do have the equation, everything changes. You can check the low energy limit to see if it recovers familiar results. You can check whether it preserves gauge symmetry. You can see if it produces strange virtual particles. You can run simulations to predict effects never seen before. An equation is both a promise and a challenge. It says, if I am correct, I will show you what happens in every situation. If I am wrong, you only need one experiment to kill me. And that is exactly what makes equations so powerful. They put your hunches on the scale, turning vagueness into testability. Every revolution in physics happened this way. Maxwell added one term to Ampere's equation and created electromagnetic waves. Einstein changed the concept of space from flat to curved and created the field equations. Dirac took the square root of the relativistic wave equation and created the positron. No one felt these solutions existed. They wrote the equations, and the equations told them. So if you want to create a new scientific hypothesis, you cannot just describe it in words. Words cannot calculate. Words cannot be tested. Words cannot be falsified. A physical theory only begins to exist when you can write an equation for it. Before that, it is only a story, and stories never open the safe of the universe. Today, if you look at the frontiers of modern physics, from string theory, spin networks in loop, quantum gravity, to gauge theory in the Standard Model, you will see a clear trend. Mathematics leads, intuition follows, and often struggles to keep up. String theory proposes that fundamental particles are not points, but vibrating strings in 10 or 11 dimensions. No one has intuition for 10 dimensions, but mathematics has no problem with it. Spin networks in loop quantum gravity describe spacetime as a discrete graph of quantum areas and volumes. Intuition screams, how can space be discrete? But mathematics only needs a suitable Hilbert space structure. Even gauge theory, the core of electromagnetism, the weak force and the strong force, is a classic example. Intuition does not tell you that electromagnetism is the consequence of U1 symmetry, that the weak force is SU2, or that the strong force is SU3. These Lie groups do not come from hunter-gatherer brains. They do not come from pictures, not from feelings, but from mathematical requirements of invariance and symmetry structure. This makes many people uncomfortable. They want physics to be visualizable, intuitive, imaginable. But nature did not sign a contract with your intuition. It did not promise to make everything easy to understand. According to human evolutionary standards, it does not adjust equations to fit your emotions. If the nature of space-time demands the gauge group SU3 kites, SU2 kites U1, then that is what we must face, whether you find it beautiful or strange. This is why arguments like "I don't like string theory because it's hard to visualize" are completely meaningless. You don't have to like it. You don't have to picture it like a 3D movie. The only thing that matters is, does it make predictions? Is its mathematics self-consistent? Is there any experiment that can test it? Your sense of visual intuition is irrelevant in that process. If modern physics has taught us anything, it is that intuition is not the compass for understanding the universe. It is a convenient tool when we live in the world of familiar sizes, speeds, and energies. But when you step into curved space, extra dimensions, quantum states, or gauge symmetries, intuition is not just wrong. It is an obstacle. It pulls you backward, forcing you to try to picture things that cannot be pictured by a brain designed for life on the African savanna. Nature does not change to make us comfortable. We must change to keep up with nature. And mathematics is the only tool that allows us to do so. It liberates us from the limits of intuition, opening up structures that are unimaginable, yet extremely precise in describing the universe. The conclusion here is simple. If you wait until intuition catches up, you will never understand. Intuition arrives last, after mathematics has cleared the path, after the model has been tested, after countless equations have been solved. Intuition does not lead you to truth. It only becomes accustomed to truth after mathematics has found it. One of the least intuitive but most important things in science is error. Ordinary people think error is a nuisance, something to avoid. But in science, error is the very soul of precision. Without error, you cannot know how correct your model is, how wrong it is, or whether it is trustworthy at all. And mathematics is what provides us with the entire structure to define, measure, and control error. Standard deviation, confidence intervals, probability distributions, parameter estimation, statistical hypothesis testing. All those things that sound dry, but are the foundation for distinguishing real science from storytelling science. If you measure a physical quantity, say the mass of the electron, and simply declare, I measured 9, 11 kachet can, what care? You have said nothing meaningful. The first question science always asks is, what is the error? Can the sedneth, to a first question science always asks is, what is the error? Those two results differ by a factor of 1,000 in reliability. Without error, you don't know whether your experiment is good or bad. Without error, you also cannot distinguish real differences from background noise. In other words, if you have no error, you have no science. Mathematics gives you tools to do what intuition cannot, measure the reliability of your own conclusions. You may feel that two samples are the same, but statistics will tell you whether that sameness is real or just random. You may think your model fits the data, but least squares analysis will show whether it truly fits or only fits in your imagination. In the lab, you may think the curve looks like a very good fit, but mathematics will ask, what is the correlation coefficient? What is the p-value? Do the confidence intervals overlap? Nature does not care whether you think the curve is beautiful or ugly. Nature only cares whether you measured correctly, and without mathematics, you cannot know that. A glorious example of the precision science demands is QED, quantum electrodynamics. This is the most accurate theory humans have ever created. It predicts the anomalous magnetic moment of the electron, called A_E, to 12 decimal places. That means you can measure a quantity many times in the laboratory and get a result that matches the theoretical prediction to within about 1 part in a trillion, 10 circumflex minus 12i. Not approximately correct, not mostly correct, but correct to the point that if the measured result deviates by 1 part in 1 trillion, you immediately know something is wrong, either in the measurement or in the theory. Error here is not an accessory. It is the alarm radar that lets us detect the difference between truth and mistake. But to achieve that level of precision, you need an enormous mathematical machinery, integrals, renormalization, complex numbers, probability amplitudes, Hilbert space, perturbation calculations, up to 10th order, 11th order, all of it built for one purpose, to match the experimental number within the allowed error. And when you see QED correct to 12 digits, accurate to an almost unreasonable degree, you realize something profound. In science, precision is not a luxury. It is a requirement. Without precision, you cannot distinguish what is correct from what merely seems correct. Without precision, you cannot tell which theory is good and which is garbage. Without precision, you cannot detect the 43 arcsecond deviation of Mercury's perihelion, a deviation so small that without mathematics it would be buried under intuition and subjective impression. And most importantly, without precision, you cannot see the places where the universe is quietly whispering to you, hey, your theory stops here. Science matures when it can measure error, and it evolves when error causes old theories to collapse. It is mathematics that gives us the language to hear those tiny discrepancies, the discrepancies that lead to scientific revolutions. In a universe that runs on numbers, precision is not merely a requirement, it is the guiding compass. When you move from the tiny world of QED to the large scale of the universe, you encounter something even stranger: spacetime. The thing we imagine as an empty, indifferent backdrop that doesn't participate in the story is actually a geometric structure so rich in computation that without mathematics you cannot even express it, let alone understand it. And that is where Riemannian geometry enters. In 1854, Bernhard Riemann delivered a lecture that almost no one at the time thought would change humanity's understanding of space. He introduced the concept of the metric tensor, a mathematical object that allows you to measure distance, not just in flat space, but in any curved space. This is not the geometry you learn in school with triangles and circles. This is the geometry of curved surfaces, spaces whose curvature changes from point to point. And what Einstein realized in 1915 was so beautiful. It is almost frightening. Gravity is not a force, it is geometry. Mass and energy curve. The metric, and the curved metric dictates the motion of matter. On the left side is geometry, curvature. On the right side is physics, energy, and momentum. Without mathematics, you cannot put those two worlds into the same equation. Without tensors, without coordinate transformations, without covariant derivatives, you cannot describe how space curves point by point. And the strange thing is, once you accept the mathematics, everything becomes clear. Planets do not follow their paths because the sun pulls them. They follow the straightest possible path in a curved space. Light is not pulled by the sun. It follows the curvature of the metric. Black holes are not holes in space. They are regions where curvature becomes extreme. This leads to the real power of mathematics. It does not merely explain what we observe. It shows us things we have never seen. When Schwarzschild solved the field equations in 1916, he found a solution describing an object with an event horizon, something many thought was just a mathematical singularity. A century later, we photographed the black hole in M87. When Feynman solved the field equations in 1922, he found a solution describing an expanding universe. At that time, no one had seen cosmic expansion. 7 years later, Hubble discovered redshift. All of this shows us mathematics does not merely describe space. It determines the destiny of space-time. Without Riemann, without the metric, without tensors, no general relativity. Without general relativity, no GPS, no understanding of cosmology, no black holes, no gravitational waves. When LIGO detected gravitational waves in 2015, the miracle was not that we heard the earthquake of space-time. The miracle was that Einstein had predicted it 100 years earlier, using only mathematics. That wave passing through us at the speed of light, distorting space by less than 1,000th the size of a proton, cannot be described in words. It can only be described by an oscillating metric. And when the data matched Einstein's field equations perfectly, we understood something Newton never had the chance to understand. Space-time does not flow, does not get pulled, is not bent in some vague way. It obeys equations. It is a living mathematical object, continuously solving equations at every point in the universe. Space-time is not merely the place where matter exists. It is the main character in cosmology. That is why I always say, if you remove mathematics from the picture, you do not just lose the explanation, you lose the universe itself. If at large scales space-time is written in geometry, then at small scales the universe is written in probability, a kind of reality that human intuition was never designed to understand. In the quantum world, there is no story in the ordinary sense, no clear path, no fixed orbit, no particle here, then moves over there as we imagine. The only thing that exists is the wave function, a mathematical object in Hilbert space that you cannot see, cannot touch, but can calculate. And that wave function contains all the information nature is willing to give you, the probability distribution of every possible outcome. When you ask, where is the electron? The wave function answers, wrong question. Here is the probability distribution. When you ask, which path does the particle take through the two slits? The wave function answers, all of them. No classical causal story applies. You can only write the Schrödinger equation, solve it in Hilbert space, and square the amplitude to get probability. That's it. Without mathematics, you cannot describe anything in quantum mechanics. You cannot describe spin without using two-dimensional vectors in complex space. You cannot describe measurement without Hermitian operators. You cannot describe interference without complex amplitudes. You cannot describe entanglement without the tensor product of Hilbert spaces. Natural language is completely helpless before these structures, not because they are difficult, but because they do not belong to the world that language evolved to describe. If you try to explain that a particle is in two places at once, you are dragging intuition into a fight it cannot win, because reality is not that the electron is in two places. Reality is that the electron's wave function is spread out, and in two places is a very poor translation into English of a complex mathematical structure. Everything in quantum mechanics is like that. Spin does not rotate, even though the name makes you think so. It is a mathematical quantity that is the representation of the SU2 group. Superposition is not the particle hasn't decided. It is a linear property of Hilbert space. Wave function collapse is not the particle chooses one state. It is the result of applying a measurement operator to the state vector. All of these sound strange only because language cannot express them without distorting their essence. But mathematics can perfectly. Mathematics says the state is a vector, an observable is an operator, the outcome is an eigenvalue, probability is the square of the amplitude, and nature nods. Exactly right. Think about this. At the smallest scale we can measure, there is no object in the classical sense, no orbit, no trajectory, no particle or wave as we imagine them. Only functions, symmetries, operators, probabilities. Reality at its deepest level is not tiny billiard balls moving in three-dimensional space. It is mathematical structures executing themselves in Hilbert space. This is not philosophy. This is the content of all 20th minus and 21 set century physics. And the strongest proof is the accuracy of quantum predictions. The hydrogen spectrum, calculated with the Schrödinger equation, matches experiment to millions of digits. QED calculates the electron magnetic moment to Kontathlushingward lasers, transistors, MRI, GPS. All of them rest on purely mathematical quantum equations. If quantum mechanics were merely a metaphorical model, those technologies would not work. You do not drive a car with metaphors. You drive with equations. When you look at how mathematics operates, both the large world of space-time geometry and the small world of quantum probability, you understand why mathematics cannot be replaced by any other language. Not because mathematics has special power, but because no other language can predict. Words describe the world. Mathematics predicts the world. And science, if it cannot predict, is no longer science. Imagine trying to describe the motion of a planet in everyday language. It moves faster when near the sun and slower when far from the sun. Or it follows a path that is sort of round, but not perfectly round. Those statements are not wrong, but they tell you nothing. You cannot use them to predict next year's solar eclipse, or the orbit of a Starlink satellite, or time dilation in GPS. But a single equation instantly gives you all of that. If you try to replace mathematics with pictures or stories, you lose what makes science powerful, the ability to be wrong. The sentence, The particle goes through both slits at the same time. Sounds fascinating, but only when you write the interference. Amplitudes can you calculate the positions of maxima and minima on the screen. Without mathematics, you cannot distinguish between a sentence that sounds good and a sentence that is correct. And if you cannot distinguish those two things, you cannot make progress. The reason mathematics cannot be replaced is that physics is not the profession of storytelling. It is the profession of prediction. This is true at every level. In cosmology, you cannot predict the expansion rate without the Feynman equations. In electrodynamics, you cannot predict antenna radiation without Maxwell. In quantum mechanics, you cannot predict atomic spectra without Schrödinger. Even something simple like free fall cannot be understood without mathematics. You can say objects fall faster and faster, but you cannot build a safe elevator with that sentence. You need a equal sign 9.8 m flaws. You need error. You need the equation. That is the entire difference between description and prediction. And if you remove mathematics, physics collapses instantly. Try removing mathematics from general relativity. You lose space-time curvature. Remove it from quantum mechanics. You lose the wave function. Remove it from electromagnetism. You lose light. You can keep the story, but you lose the universe. Sometimes I hear people say, I want to understand nature without mathematics. That is like saying, I want to learn to swim without getting in the water. You can stand on the shore, imagine how to swim, describe arm movements, even tell stories about water, but you will never swim if you don't jump in. And in science, jumping into the water means writing equations. You must immerse yourself in mathematics, because that is the environment in which nature operates. The more you resist it, the farther you stay from truth. So the conclusion of this part is simple and uncomfortable for anyone still hoping for a shortcut. Demanding to understand nature while abandoning mathematics is like demanding to swim while refusing to enter the water. There is no other way to approach truth. In this universe, mathematics is not merely a tool. It is a prerequisite. When you look back over the entire journey we have taken from the way science begins with a conjecture to mathematics turning conjecture into a testable model, from vague theories being eliminated because they cannot be calculated, to the miraculous ability of mathematics to see ahead of reality, from the unreasonable precision of QED to the majesty of Riemannian geometry describing spacetime, from the probabilistic world of quantum mechanics to the limits of human intuition. You realize something important that science has been whispering to us for 400 years. Nature does not write poetry. Nature writes equations. Everything we observe, light, force, matter, space, time, operates according to mathematical structures so tight that if you remove mathematics, you do not just lose the explanation, you lose the phenomenon itself. Electromagnetic waves do not exist without Maxwell. Black holes do not exist without Einstein. Electrons do not exist without Schrödinger and Dirac. Even the concept of path in quantum mechanics cannot be expressed in words. It only has meaning when you write the path integral. When you look at the universe with natural language, you see stories. When you look with mathematics, you see mechanism. And that mechanism does not care whether you find it beautiful or strange. It only cares whether you wrote the correct equation. The extraordinary thing is not that mathematics can describe the universe. The extraordinary thing is that the universe operates with mathematics, as if the equations are the laws it has obeyed from the beginning. We did not invent mathematics the way we invented the light bulb. We discovered it the way an archaeologist discovers a buried city. Arithmetic was not created. It was already there when galaxies formed. Geometry was not something Euclid thought up in his spare time. It is the structure that space has obeyed since before Earth existed. Lie groups were not made up by mathematicians. They are the skeleton of physical symmetries in nature. When Maxwell wrote his equations, he did not create light. He merely translated the structure of light into symbols. When Dirac wrote his equation, he did not create the positron. He merely read its existence from the structure of mathematical space. When Einstein wrote the field equations, he did not create curved spacetime. He merely said in symbols what the universe had been doing for billions of years, letting energy determine the shape of the very stage on which physics plays out. Looked at this way, mathematics is not a language we impose on the world. It is the language the world uses to exist, and we are merely slow students trying to decode it. I often joke that nature is the strictest teacher. It never explains in words, never repeats itself, never says what I mean is, never gives illustrative examples. It only gives results and watches to see whether you can find the equation that explains them. And if you write the wrong equation, it does not punish you. It simply ignores you. This leads to one of the greatest lessons science teaches us. Every model is wrong somewhere, but some models are wrong less and over a wider range. Newton was wrong at Mercury, but correct for everything else he could observe. Einstein was correct at Mercury, at bent light, at gravitational waves, but may be wrong under extreme energy conditions, near singularities. Quantum mechanics is extremely accurate in describing electrons, photons, chemical bonds, transistors, lasers, but may not be complete for describing black holes at the Planck scale. And mathematics is the filter that lets us know which models can still withstand the pressure of experiment. But more importantly, mathematics is where the next model will be born. Without mathematics, no new equation can be created. Without new equations, no new theory. Without new theory, no progress. Every leap in physics begins with the question, is there a better mathematical structure to describe this? And that very question shows us that the universe does not operate on feelings, but on laws so profound that the only thing that can reach them is mathematics. Nature is not designed to be easy to understand. It simply is. Our task is not to make it simpler, but to develop a language strong enough to read it. And after 20 parts, after the journey from initial conjecture to space-time geometry, from quantum probability to gauge symmetry, we can say one thing clearly and bluntly. Nature does not speak English. Nature speaks mathematics. You may not like that, but if you want to understand the universe, truly understand, you must learn the language it uses to write itself. If you have come this far with me, through the initial conjectures, through the equations, through the tiny but decisive errors, through the curves of space-time, and the bizarre probabilities of quantum mechanics, perhaps you have already felt something that I often struggle to convey to my students. The universe is not a novel, not a story, not a poem. It does not try to make sense in the way humans desire. It simply operates. It simply is itself. And if we want to understand it, we must learn to speak to it in the exact language it uses, the language of mathematics. Now you may ask, sir, if mathematics is the language of the universe, how much do I have to learn? And I will answer with a sentence I believe is completely sincere. You learn to the extent that you want to converse deeply with the universe. You do not need to become Einstein to feel the beauty of a single equation. You do not need to become Dirac to know that one formula can say more than 1,000 words. You only need to open your mind to the idea that this world may be stranger than you ever imagined, and that you can understand it simply by patiently speaking to it in its own language. I always have the feeling that the universe, vast beyond imagination, is actually a gentle friend. It does not cruelly hide its secrets. It lays them out everywhere, in the way light bends, in the way electrons jump between energy levels, in the way Mercury creeps backward across the sky, in the interference fringes on the double-slit screen, in the tiny ripples of gravitational waves passing through your body without you noticing. But the universe says those things with equations. It does not say, hey, I'm curving space here. It writes and waits to see if you are curious enough to decode it. It does not say, hey, light is actually an electromagnetic wave. It writes 4 Maxwell equations. It does not say, hey, atoms have discrete spectra. It writes the Schrödinger equation. It does not say, hey, I'm hiding an antimatter particle. It lets Dirac write an equation with a negative solution. And it does not say, hey, I ripple every time 2 black holes merge. It sends a signal smaller than 1,000th the size of a proton, and watches whether we are patient enough to measure it. Understanding the universe is not about making it simpler. Understanding the universe is accepting that its essence lies in structures we must learn, must discover, must change ourselves to approach. I once told my students that when you learn the mathematics of physics, you are not learning to solve homework problems. You are developing a new pair of eyes, a new sensor that detects things invisible to your natural senses. When you learn Riemannian geometry, you begin to see curvature. When you learn quantum mechanics, you begin to hear probability amplitudes. When you learn field theory, you begin to feel the way symmetries govern every law. These are not magic. They are the result of learning the language the universe uses to write itself. But remember this, no one sees the whole picture. Einstein did not see the whole picture. Dirac did not see the whole picture. I and you and all of us, we only see a small part of the canvas. But that is not sad. That is exactly the reason to keep asking. I do not want to end with comfort, because science has no obligation to comfort anyone. I want to end with curiosity, because curiosity is the only thing that has taken humanity from stories around the campfire to writing equations that describe the curvature of the universe. So I will ask you this. If mathematics is the language of the universe, how far will you learn that language? Far enough to read the simple sentences, far enough to converse, or far enough to write a new sentence, an equation no one has ever seen, and let the universe confirm it with a phenomenon no one has ever observed. I don't know how far you will go. No one knows. But one thing is certain. You cannot converse with the universe if you refuse to listen to it first. And it speaks very softly. It speaks in derivatives, in integrals, in tensors, in probabilities. It speaks in equations. If you enjoyed this journey of discovery, please subscribe so you don't miss the next parts. See you again in the next adventure with the universe and its equations.